give a talk, Justice?
Sure, yeah.
Great.
I will share my screen. Okay. Cool. Okay, so hi everyone. This is work I did at MATS over the past winter with Davidad, and it is synthesizing gatekeepers for safe reinforcement learning. Okay, so how will we know when we've achieved safety? If we can do really well on safety evals, does that mean that we're safe? No, right? So the idea of provable AI safety tries to get a grasp at how we answer how we will know when we're safe. So let's look at the high-level threat model that we're interested in. So we have AI companies racing for AI supremacy with little regard for safety. And the high-level theory of change is that we want to turn that prisoner's dilemma into a stag hunt by requiring that companies satisfy safety benchmarks, which then issue some certificate that once they've passed these benchmarks is a certificate that anyone can check. Other companies, the government, the public can check that they've achieved safety after passing these benchmarks. So what does this look like? So one notion that has been talked about is a safety gatekeeper, which is a few things. So it is an AI generates a policy in the context of reinforcement learning and a proof that that policy is safe for some definition of safety. And then a verifier, the gatekeeper has a verifier which checks the proof. And if it verifies, then the gatekeeper can use the policy. And if the proof isn't true, then it just rejects the policy. Sort of second simpler version of a safety gatekeeper. Oh, sorry. The proof that generated by the AI is probably something complex, very complex, but the verifier is a simple human written program that just checks the logic. A simpler version of a safety gatekeeper in the context of RL might be something which just accepts or rejects an action that an RL agent takes in the world, depending on if it's safe or not to take that action. So let's look at one way that this can potentially be used. So model checking is a formulation which verifies whether a finite state system meets some specification by exhaustively searching over all possible next states that the system can be in according to the dynamics of the system. So we can specify using temporal logic, something like the formula here, which is X is in A until X is in B on time frame S to T. And then eventually on T to U, X is in C. So a model checker can take that specification and verify whether the system satisfies that. And if it doesn't, then it can provide a counterexample trajectory, which could be used potentially for downstream learning tasks. So model checking, again, it only works for finite state systems. But if we can make a system, if we can make a subcomponent of a complex task amenable to model checking, then we can use it for these subcomponents. This has been done, for example, in flight critical software, where the braking system for aircraft has been checked to satisfy the specification. So let's look at a simple example that I did. So we have this inverted pendulum problem where the state space is the angle and the angular velocity of the inverted pendulum, and we're trying to keep the pendulum between negative phi and phi, the angle between negative phi and phi. So the failure region is outside that, negative phi and phi, so that's colored in red. Then, sorry? Okay, the yellow and green are considered the constraint region, so that's just not failure. But the yellow region is part of the state space where the angular velocity is too large, such that no action that you take can lead you away from the red. So when you're in yellow, you will eventually be in red no matter what. So we want to be in green, where there's always an action that we can take to remain safe. So because cart pole is not a finite dimensional system, a finite state system, the angle exists on the real line. We have to somehow make it amenable to model checking. So in order to do that, we discretize the state space. So we get some finite set of states from that. And to solve this, we can do a simple reinforcement learning where we specify a reward of 0 on the failure region, red, and then a reward of 1 on everything else. And so we only know the boundary between red and yellow, which is specified by negative phi and phi. But we really want the boundary
the
between...
kind of prototype where all of this works is what Junliang already talked about, which is the Beauville decomposition for abelian schemes. I'm going to erase this.
Sorry, I didn't catch that.
So maybe so that kind
of
I think Matthew accidentally has his mic.
sample case.
Okay. I will continue then. Okay. So we want the boundary between yellow and green, but we only know the boundary between yellow and red. So once we've specified the reward, we can run policy iteration, which is guaranteed to extract the optimal policy, but also the optimal value function. And an interesting thing about the value function is that it gives a higher value for the green states than it does for the yellow states, than it does for the red states. So the value function itself gives us a way to discriminate between green and yellow. So the gatekeeper can use this value function to check whether an action will transition from green to yellow and then just reject that action and only accept actions that remain in the green. So this is one method of model checking. The cart pole and inverted pendulum is still a simple problem, and it's amenable to discretization. But when you have systems which have larger dimensionality, then we can't just discretize. I mean, really, discretization works for maybe 5 dimensions. Beyond that, it's more difficult. So I was also interested in knowing if we can get a sort of discriminator between safe and unsafe, like green and yellow, using in continuous state systems directly rather than appealing to discretization and model checking. So the next thing I looked at was the use of a control barrier function, which does that. So if we look at the figure on the right, control barrier function looks something like that, where it's a control barrier function is positive where the system is safe and negative where it's unsafe. And that boundary defines the safe set. So a control barrier function guarantees the existence of a safe action for any point in some region defined by the CBF. So there are some caveats with this. First is that we have to know the dynamics exactly. So they're deterministic dynamics that we have to know. There has been extension to this into stochastic dynamic systems, which I'm definitely very interested in and want to pursue soon. Another caveat is that the dynamics have to be affine in the control. So here we have a dx dt equals f of x plus g of x times u. So it's affine in the u, which is the control. This might seem like a restrictive assumption, but actually f and g can be nonlinear in the state x. So it's not so bad of an assumption. We also have to know the failure region exactly, just like in the previous problem. So this control barrier function can be used by a gatekeeper if we have a proposed policy and this control barrier function, the gatekeeper can run the policy forward and check if the states are positive under the control barrier function, and if they are, then the policy is safe. But if the policy ever gets negative on the control barrier function, then it's unsafe. So the CBF is part of the proof, essentially. It could be part of a proof that a gatekeeper uses to verify the safety of a policy. So an explicit example of a CBF is consider a 2D particle traveling from point A to point B, and we want to avoid a circular obstacle shown in the bottom right. The obstacle here defines the failure region. Because the obstacle is a circle, the equation of the circle gives us the failure region. So x squared plus y squared equals r squared, right? If we're inside the circle, then that's failure. If we're outside the circle, then we're safe. So x squared plus y squared minus r squared is the control barrier function, because that it's positive outside the circle and negative inside the circle. I learned an extra parameter which basically defines how conservative the resultant trajectory, this blue trajectory, is, like how close or far it is from the circle. But ultimately, because of the geometry of this obstacle, we just know we know the form of the CBF, so we can directly extract safe trajectories using this the control barrier function. So not all failure regions in the world are circular, so we might want to learn the failure region through sampling or some other method. So that's another aspect or part of future work that I'm interested in doing. Ultimately, in provable AI safety, we want to do this. We want to scale this to large dimensional systems. So a follow-up I did was doing this on a quadrotor, which has an 18-dimensional state space with more complex dynamics, which are still affine in the control, but they're more complex, and it has the same fundamental goal. But this is still a work in progress. But ultimately, I want to see how far we can extend these methods to large systems, and ultimately, for future work, I want to do dynamic obstacles and get probabilistic guarantees for systems with stochastic dynamics, as well as learning the control barrier function using by sampling irregular failure regions while the system is running. And last thing is also applying this to safety critical systems such as electrical grids or nuclear power plants. So the failure region there might be avoiding a blackout. So yeah, thank you to all the people who helped me out with this. Roman, Carson, Davidad, and Laura for help. Thank you.
Awesome.
Yeah.
That's great. We can take a few minutes, even 10 minutes for Q&A and general discussion around this work.
Yeah, Raphael, I think you have a question.
Yes. Hey, thanks, Justice. This was obviously very very germane, and like especially in the way the type of model that you've built here. It's kind of very directly analogous to the stuff that I'm working on, that we're working on at the Spark project. So it's great to see it framed here. I would love to hear, first of all, I'd love to hear a little bit more on the role of the proof here. I mean, I think it's very clear how the control barrier function or any other kind of like reward function that has a cutoff can play a role in can be used to determine a gatekeeper. But to me, it seems like if you have the system and you have like the policy and the gatekeeper has a world model that it can run simulations under or do some form of analysis under, then that takes the role of the proof. So is there a specific way in which you all use this concept of separating the proof and the verification, the proof generation and proof verification here, or is that all bundled together in this framing?
Yeah, thank you for the question. Yeah, so I didn't explicitly separate the proof and the policy or I didn't separate these things out. I wasn't really looking at proofs or generating proofs or verifying them in this work. This is sort of not my goal here, but some like an idea that can be used potentially for future work. I mean, the control barrier function for this example is some artifact which could be used in a proof which I haven't generated or anything like that, but is some artifact which defines safety. So I am interested in like how these proofs work and how the verifier for that would look, but I haven't actually worked on the proofs themselves. Yeah.
Got it. Thank you.
Yeah. Yeah, Paulius.
Yeah, can you hear me? So I was wondering, so in usual formal verification literature, the sort of the safe specifications are given by domain experts. So like there are some like I think in general just like the literature on formal verification seems quite limited. The usual applications are like in this, I think the paper that you linked with this like aviation, and there's been work by Guy Katz from Stanford, and they invented like neural network verification stuff, and that was also applied to aviation scenarios. So basically my question is, what's the plan for like learning these specifications perhaps? Because everything so far, even these sort of toy models that you show, these are like sort of mathematical toy models, but you know, as you mentioned yourself, you know the sort of the safe and the unsafe regions. Any clue on how these the safety criteria can be learned?
Yeah, so well, I guess the way I've been thinking about it is that we have a particular failure in mind that we want to avoid, and we do specify that failure like itself. I think that potentially if you could I mean, in some sense, you have to know, like you have to know what the failure is in order to avoid it, right? Like if some yeah, I mean, everything that I've been doing has been under the idea that you know the failure region. Potentially you could take samples from the environment, which you can take samples from the environment, and then if you reach some state that is a failure state which you don't know the boundary of, then you can like learn the failure region in the simulation. So you wouldn't obviously execute this in the real world, but you have some world simulation, and then you execute an exploration policy in this simulation, and then you sort of learn the boundary of the failure region, potentially using a neural network or some like zonotope formulation or something like that. But yeah, this is work that I haven't investigated much, but I am interested in.
Okay, cool, thanks. And so you also mentioned here temporal logic. There's been also work in a slightly different vein than like the classical neural network verification, where people use different kind of temporal logics to formulate these specifications and then use model checkers to prove some safety parameters. But from sort of David's plans that I've seen, it seems like, I don't know, it seemed like these kind of like counterexamples or proofs that would be verified by these model checkers are not enough, perhaps, but or did I misunderstand this? Like any clue on this?
So sorry, not enough as in there might be failures outside of.
I suppose like when I'm looking at David's like these plan graphs and whatever, which are very intricate, there's like a lot of mention of like that it seems like a reinforcement learner will learn the proof somehow to generate a proof. And so it seems like the model checker, I don't know, is like in the second plan or something.
Sorry, I still don't understand. The model checker is separate. And yeah, I mean, I guess the idea is that the AI generates the proof, but this model checker doesn't need to be AI generated or anything complex. It just checks that the logic holds.
All right, so reinforcement learner would generate the proof and just outsource it to the model checker, then which checks if it's correct.
Right, yeah. That's a high level, yeah.
Right, okay.
Thank you. Raphael, did you have a second question?
No, I had a comment on that last question about the failure region.
Yeah.
Yeah, I did want to comment that one way to think about it is so you have a region of your state space that you would like that ultimately you would like to characterize it as safe or unsafe if a certain function of it crosses a threshold or whatever. But if that function is itself uncertain, then it's better to look at it as a probability distribution in the joint of the quote unquote outcome, which can be a loss or a reward, and the state, right? And then you can use the math actually makes itself simpler because you can just read it as a problem of joint inference on those two things, and then marginalizing on the outcomes, because ultimately you don't actually care about the microstates, if you will. Sorry, marginalizing on the states. So you can think about it as marginalizing over microstates to just get at characterization of which policies are lossy or not. That helps. And a complete application of that is you can, like, if you think about like a complex real world system where it's really impossible to think about all the different failure modes, they're combinatorial and very path dependent, then what you actually want is to find heuristics, is to find bounds, is to find dead ends. And a really useful way to do it is to generate a bunch of those and like have some ways to incrementally have cheap checkers and defense in depth of those cheap checkers where some of them can be humans. You can just show them to people and they say, well, yeah, that's obviously dead end. I wouldn't trust that state. right? And some of them can be simulation based, right? Drive push forward on those from those states and find that there's a failure modes almost always, and then you just like learn to exclude that region.
Right. Cool. Thanks.
So I had one question, which is I really like your red regions and your yellow regions. The yellow regions being those that you can't escape from the bad place. And that seems like a nice mapping. So given the dynamics and given a bad region, you can sort of define a mapping from that region to the yellow region. And I'm wondering what the complexity of the yellow region is, because as you're, if you do want to make a proof certificate, you'd like it to be fairly simple. And so you're going to probably have to, do an outer approximation of the yellow region. And I wonder if you've thought at all about what the complexity of that mapping is.
Yeah, that's a interesting question. I don't know offhand. I haven't looked at what the sort of complexity of this region looks like. I yeah. Sorry, I don't think I have. Yeah.
Like in your circle, do you have a sense of what that region is for the, you want to avoid the circle. Is it a bigger circle or is it some, could you get like a fractal structure out there or something? Or I don't know.
Yeah. Oh, yeah. No, I don't actually know. It definitely depends on the dynamics. Yeah.
So in the general case, this reduces the problem of finding attraction basins, which is irreducible.
And some of those basins can be really complicated.
Yeah, exactly.
Great, thanks. Great talk.